Isomers are molecules with the same formula but different arrangements. We have two major groups. We have constitutional isomers, which have different connectivity, and stereoisomers, which have different spatial arrangements. Stereoisomers can be further broken down into two major groups. We have configurational isomers, which we interconvert between those by breaking bonds. And we have conformational isomers. With conformational isomers, a huge focus is going to be on the energy levels of each structure. So how does the energy level differ if we just rotate this one bond 60 degrees versus another 60 degrees versus 180 degrees? Looking at what is our most stable versus least stable configuration. We can look at these with Newman projections and cyclic conformation, so our chairs. This video is going to be a complete guide to everything you need to know about Newman projections, how to go from Newman to bond line to Newman, as well as the different rotations, their names, and respective energy levels. I drew this molecule here, but I also represented it as a 3D structure. We're going to call these little green molecules carbons as well. So you can see that we have a 4-carbon chain. I'm going to name these carbon 1, 2, 3, and 4. So this is our carbon 1. This is carbon 2, this is carbon 3, and this is carbon 4. If we have to draw a Newman projection looking up carbon 2, so we are looking at the carbon 2 to carbon 3 bond, the first thing I do is I look at it horizontally. So it was bent before, like just kind of at an angle. I'm going to switch it. So the bond that we are looking at is just directly horizontal. If you don't have an iPad with you, move your piece of paper, okay? This is how I initially started practicing it and how I ended up getting really good at it. All I'm doing is rotating it so that the bond I am looking down is completely horizontal. What an actual Newman projection is when we look at it from the front. So we are looking directly like this. We can completely see our front carbon. You can't really see the back carbon because it's directly behind carbon 2, but you can see what's coming off of it. We see these hydrogens hanging out to the side, and we see this green carbon coming down. When we draw Newman projections, this little dot right in the center, that is going to be our front carbon. So that little dot is our carbon 2, the carbon that we are looking directly at. And then this big circle in the back is our back carbon, our carbon 3. This is how we would draw our front carbon, is going straight up. We have our green molecule, and then coming off the sides of it, we have our hydrogens. And again, we can see that here. Coming straight up off of it, we have our green molecule. Coming out the sides, we have our hydrogens. Looking at our back carbon, coming straight down, we have that green carbon. Coming up off the sides, we have our hydrogens. And this is the same thing that we see here. Coming straight down, we have our green carbon. And then out the sides, we have our hydrogens. So if you are given a bond line and asked to create a Newman structure, the very first thing that I would do is reorient your paper or your iPad or whatever you're using to look at your bond horizontally. This makes it so much easier to see what is directly in the plane. So whatever is in the plane, we are drawing like this, and then these guys are coming out to the sides. This will allow us to see if it's coming up or down, if it's in the plane or out of the plane. When we were going from Newman to bond line, I said, start by making this horizontal, and then we can see exactly what's coming up or through the sides attached to each carbon. We're going to do that exact same thing. So this is my front carbon, and this is attached to my back carbon. So this guy is correlating with this. Right now, we are going to focus on what is in plane with these two carbons, okay? Because the ones coming out to the side, these are going to be on wedges and dashes. We can just add that at the end as like substituents coming off of these carbons. But for right now, I want to focus on what is happening here on this front carbon. In plane with this front carbon, coming up off of it, I have a tert butyl. This back carbon coming straight down off of it, I have a methyl group. So I'm going to just indicate that like this. Just to be sure I am transferring this right, always count your carbons. Like please always count your carbons just to double check. So I'm going to do one big parent chain. So this will be carbon 1, 2, 3, 4, and 5. And as we can see off of carbon 2, I'm going to have 2 methyls coming off of it. I don't really like working with like tert butyls and isopropyls. Kind of confuses me. So I just number my carbons and I see that I have a dimethyl on carbon 2. So carbon 3, this is carbon 3. In the plane with carbon 3, I had a tert butyl. How I like to remember wedges versus dashes in Newman projections is the Majority of our population is right-handed, okay? So a huge bulk of our population is on the right or right-handed, however you want to think about it. So it is going to be a huge, like, bulky thingy, which is a wedge. Whereas we have a couple scattered people left-handed here and there. So that might be represented by dashes, okay? So it's not a huge bulky thing facing to you. These are kind of like away from you. Here and there, we have our little lines depicting it. So to the right, I have my wedges. To the left, I have my dashes. So coming off of carbon 3, which is this guy right here, I have chlorine facing towards me, and I have hydrogen going away from me. Now on carbon 4, so this big guy right here, I have a hydrogen, my bulky right side, my big bulk of the population on the right. And then my scattered few who are left-handed, my dashes is going to be my ethyl. So I'm going to do a little hydrogen here and then an ethyl on a dash. This is typically how ethyls are drawn on dash configurations. If you don't know what an ethyl is, it is a 2-carbon substituent. So this is carbon 1, carbon 2. This is carbon 1, this is carbon 2. I just did this numbering to help us go from Newman to bond line, but this is not the correct numbering when we are actually naming this compound. So just be aware of that, because the actual name of this, our main parent chain, is going to be our longest chain of carbons. So because I have a carbon here and a carbon here, my longest chain of carbons would not be 5 carbons long, it would be 6 carbons long. And instead, this would be a methyl group substituent. We would not have ethyl as a substituent, we would have methyl as a substituent. Most of the time, you are going to be asked to make a Newman from a bond line when looking to the right. So whether you are looking up this bond or looking down this bond, as long as it's generally to the right, that's when our wedges are right, okay? You can kind of think, so this is me, I'm facing this direction, okay? This is my right hand. This is my left hand. My wedges come out towards me. My dashes are going away from me. So that's typically why this works. If you can't conceptualize it in your head and understand where are my hands, which way is it coming out, if you're looking towards the right, your wedges are going to be on the right. So my OH and then this methyl group are here. So if you're being asked to look from carbon 3 down carbon 2, so we have 1, 2, 3, you are being asked to look down here. So now you are standing facing the opposite direction, which means that your right hand is going to be over here and your left hand is going to be over here. So it's just going to be flipped, okay? If you can't conceptualize it, if you can't stand in your room, figure out which way is like right, left, wedge, dash. If you can't conceptualize it, if you're looking any way to the left, flip it. So just be very, very careful of that. Be aware of which way you're looking, but it is most common. That's why I said your wedge is always going to be on the right. They're not always going to be on the right. It's just most of the time you are going to be asked to draw the Newman structure from the perspective of the right side. When there is no overlap of atoms in our line of sight, it is called staggered. So when we look down our carbon 2, I can see all of our atoms coming out the sides and up the top. No one is blocking each other. This is like really specific, but if you've ever seen like a dance recital for little kids or just in general, if they form 2 lines, the front line is going to form little windows so that you can still see the girls in the back line. They are staggered. So even though there are people in the back, you can still see them from the stage. I hope this resonates with more than just a niche group of people, but that's a good way I like to think about staggered. Everyone is in their windows and we can see everyone no matter if they're in the front or the back line. We've already covered how to draw this exact conformation. So this is in the staggered conformation, but this specific one where we have our 2 largest groups, so carbons are obviously larger than hydrogens, our 2 largest groups are 180 degrees away from each other. They are nowhere near each other. This is called anti-conformation. The full name is anti-periplanar. So anti means opposite, peri means around, and planar means the plane. So they are on opposite sides of the plane. This is our most stable conformation that you will ever see in Newman projections. Your 2 largest groups are as far away as possible. For this next example, I am leaving the front carbon the same. What I'm going to do is rotate this back carbon. So I'm just rotating our back carbon, leaving the front carbon the same. I am rotating our back carbon once. So now when we look at it head on, we can still see all of our atoms, all of our little dancers are in their own windows. However, our 2 largest groups are now only 60 degrees away from each other. So it is still staggered, it's still pretty stable, but now we have some interactions going on with our 2 largest groups. we see that hydrogen coming straight down, and we see this carbon and this hydrogen coming out the sides. So with this conformation, we have our two largest groups near each other. Now, this is still staggered, so it's pretty stable, but now we might have some interactions going on, whereas here there was absolutely nothing happening between the two. They're kind of in an awkward state. So it's staggered, but it's not really that stable. So it's going to be called gauche. It's kind of an awkward word. Hopefully that might help you remember it. This is how it is spelled. So this is our gauche conformation. Just to do a quick little recap with our two staggered conformations, they're both pretty stable because there's no overlap in our atoms in our line of sight. However, this is our absolute most stable, our anti-periplanar conformation, because our two largest groups are furthest away from each other. And then, although this guy is still stable, he's slightly less stable because now our two largest groups are kind of next to each other. Again, they're not overlapping, but now they're closer together. This will cause some interactions, causing it to be less stable than the anti. Now we are going to look at our eclipse conformations. So I'm just going to be rotating this back molecule once again. So starting at our anti-staggered conformation, if I rotate this a little bit, all of my atoms are overlapping. When we are looking at this, looking at it from the front, we can really only see the front carbons. They are completely eclipsed, like a solar eclipse. I'm going to draw it pretty much exactly like this, okay? I want to show that these guys are behind it. So that hydrogen, that top hydrogen, is hiding behind our front green carbon. We have another hydrogen hiding behind this hydrogen. And now we also have our green carbon hiding behind that hydrogen. Now I want you to notice that these two, our two largest groups, they're still 120 degrees away from each other, okay? It's eclipsed. They're all pretty high in energy, kind of unstable. This is like, I would compare this to if you go to a movie theater and it's like a pretty empty theater. And of course, out of all the seats, a group of people comes in and sits right in front of you. Are you going to be mad? Yeah, like literally move over. So you're going to be pretty unstable, a little bit high in energy. You're going to be pissed off. You're going to want to move around. So our eclipse conformation is going to be higher in energy than our staggered conformations. Now I'm going to rotate again. So if I rotate a little bit, here we are in our staggered gauche conformation, and I'm going to rotate a little bit more. We are totally eclipsed. Our two largest groups are completely overlapped. To represent this in a Newman projection, once again, I'm going to show that my two largest groups, so my other green carbon is directly behind my front green carbon, and then my hydrogens are directly behind those hydrogens. We can compare this to, again, if you go to a movie theater, it's pretty empty, and of course, a tall dude comes in and sits directly in front of you. How pissed are you going to be? You can't see anything. This is what's happening here. Okay, this is me. This is the tall guy who came and sat directly in front of me, even though look at all the seats that were available. He could have sat there. He could have sat there. He could have sat there. But of course, you had to sit right in front of me. So you're going to be super pissed off. You are going to be super high in energy. You're going to be very excitable, very unstable. Another thing I want to mention about this is that this is also called syn, S-Y-N. This prefix can also mean same. So as we saw before, when they were direct opposite one another, this was called anti-periplanar. So syn means same. So this conformation is called syn-periplanar, same side around the plane, okay? So this can either be called totally eclipsed or syn-periplanar as well. And this is our least stable conformation. And again, both eclipsed conformations, not stable, but this one specifically is the highest in energy because it is the most unstable. In classes, you are going to be looking at an energy diagram. So I'm just going to kind of explain what's happening. This is low energy. This is high energy. We already talked about how our staggered conformations are pretty low in energy. That's these guys right here. Our gauche conformations are pretty low in energy, but our absolute lowest in energy is going to be our anti-periplanar. All of our eclipsed conformations are our highest in energy, which we talked about. You're at the movie theater, you're pissed off, okay? You're unstable, you're high in energy. So all of these tall peaks are going to be our eclipsed conformations. But again, regular eclipsed, still high in energy, but lower than our absolute most pissed off guy is our syn-periplanar, where our largest groups are completely overlapping. So that guy is going to be the absolute highest in energy. And our anti-periplanar is going to be the absolute lowest in energy. This is it for the video on Newman projections. I hope you all enjoyed, and I will see you in the next one.